Welcome to Mr. Math Academy. Grow your math brain.
Hello friends, welcome back to Mr. Math Academy. So today in this video we'll discuss about the stress strain curve for a ductile material. So generally we are taking here mild steel as a ductile material here, which is a low carbon steel. So generally what happens when the member is subjected to a load, external load, okay, there will be a deformation takes place. So there will be deformation takes place means the longitudinal dimensions will be increases, but the lateral dimensions will be decreases. So means what, there will be a development of the strain will be there because of the changes in the dimensions here. Okay, now there is one more term is there, that is the stress here. So this stress is nothing but it's a load acting per unit area. So load acting per unit area means it's an internal resisting force which is developed inside the body per unit area, that will be the stress. Now we just see, so which is the cause and which is the effect. So cause and effect means, if suppose when you apply load here, if suppose I am taking this is a member here, any mechanical material or member, so if it is subjected to a load on either direction, so what happens, there will be a deformation takes place in the longitudinal way. So the lateral dimensions will be decreases. Okay, so finally it may be like this. So when the member is subjected to a load, so means what, the longitudinal dimensions will be changes and the lateral dimensions will be decreases. Means what, there will be a strain will be occurs in the material, so which gives the changes in the dimensions. Okay, there is one more term called, that is a sigma, that is nothing but a stress here. So which is nothing but, so this stress is developed inside this body to resist the strain here. Okay, to resist this strain there will be a term called stress which is developed inside this body here. Okay, now we just come to know that, so this will be the cause here. Because of this strain, we can just see there will be a stress in the member. Okay, now this will be acts as some effect here. Okay, now the first term is epsilon here, that will be the strain, because when the member is subjected to a load, so there will be a deformation takes place. So means what, there will be a strain in the material. Okay, now this will be the cause, it will be acts as a something like input to the member here. Okay, now because of this cause, like input to the member, the output is nothing but like stress which is created inside the body which resists the strain here. So now this will be the effect here. Now again, this is the one term how we can represent here, which is the cause, which is the effect. Okay, there is other term like in other way we can explain this. So sigma is a function of strain. So sigma is a function of epsilon means the stress is a function of the strain, because strain is a independent one, but the thing is the stress is a dependent on the epsilon, dependent on the strain here. Because for general example, okay, now this is, I think this is, you have got this is the one more way how we can understand this too. So this is the first method how we can understand how the stress and strain will be related here. Second thing is, with this help we can come to know which is the first and which is the second, like that. Okay, now what happens, we'll come to know this. Okay, we'll go for this one, like a stress strain curve here. So this will be the curve that what we have got in the, with the help of the, when the member is subjected to a test like tensile state in the universal testing machine. So generally what we have taken here, it's a mild steel material, that is a MS here, so which is a ductile one. Now what happens, so you just see these are the points here which are represented here, O, P, E, Y1, Y2, U and F. Okay, now in this graph we'll just analyze how this graph comes. Okay, now what are the salient points at each and every point, what will be the condition of the material, like that we can go here. Okay, so now in this case what happens, when the member is subjected to a load, deformation takes place, strain is there, okay, stress will be there. So means what, at some particular point when the load is applied, so the thing is the stress will be directly proportional to strain, because the stress is dependent on the epsilon, that is the strain here. Once if the strain increases, stress will also be increases. Once if the, again if you apply more load, again the strain will also be increases. Means what, elongation increases. At the same time the stress will also be increases. That's why, so at some particular point what happens, okay, the stress is directly proportional to strain. To some extent the stress is directly proportional to strain. That's why when you draw the graph, okay, so you just see from O to P, we can see something like linearity we can see. Okay, the material behaves like some in such a way that the stress will be directly proportional to strain. So means what, we can see the somewhat like straight line from O to P here. Okay, now this indicates, so here the P indicates it's something like proportionality limit here. Okay, this P indicates, I'll just represent here, this P indicates it's a proportionality limit. So proportionality limit means that is a linear behavior will be there with respect to the stress and strain. So now you just say stress is directly proportional to strain. Now what happens, the next thing is, if you just remove this proportionality here, it becomes stress is equal to strain. The thing is, when you remove the proportionality here, so we should be having some constant here. I'll just take this as a sum E. Now what happens, again you just cross multiply here, so this sigma by epsilon is equal to E. Okay, now this E is nothing but it's a Young's modulus here. This E represents Young's modulus of a material. Now what is the Young's modulus means actually? So it is a measure of a stiffness of the material. Now how we can calculate this Young's modulus with respect to this graph here? Because we know that A is equal to stress by strain here. Now what the thing is, if you just take the slope here, okay, if you calculate the slope in this, means within the proportionality limit we have to calculate the slope so that we can get the Young's modulus for this material. Okay, now up to O to P, what happens, the proportionality limit will be there. Now the very next important point is what happens when the load is applied, the elongation takes place. The next thing is, if you just remove this load what you have applied, again this material will come back to the same shape here, that is the original shape and size. So it's nothing but the material will be in a, that is a, it is in a elastic limit only. So means what, it is having some elastic property. So up to the point P, when you apply the load, deformation takes place. Again when you just remove this load what you have applied, the material come back to the original shape and size. So that's why this P is nothing but it is under the, okay, elastic limit itself. Now this stress and strain, like stress is directly proportional to strain, this is nothing but actually it's a Hooke's law. This stress is directly proportional to strain, it's nothing but a Hooke's law, that is applicable only within the elastic limit. So this P is not the elastic limit. Okay, if you just move, okay, above from the P, okay, if you apply some more load, what happens, again there will be a deformation takes place. Now what happens at point E, so that is from P to E, so we can just see something like there will be a small curve will be there. So now it is not a linear, that is from P to E. So here from O to P it will be a linear behavior will be there, but when it moves from P to E, you can just see somewhat like curve here. So means what, this stress is directly proportional to strain, that is the Hooke's law will be obeyed within this P only. Okay, within this P, that is a proportionality limit, this Hooke's law will be obeyed. So after that, so Hooke's law will not be obeyed for any material. So within the proportionality limit we have to take. Okay, so within the proportionality limit. Okay, next I will go for the point E. So point E is nothing but there will not be a linear, we cannot see the linearity here, but the thing is what happens at point E also, there will be a, okay, if you just remove the load again at point P, again it come back to the same shape and size, that is the original dimension, and original dimension it we can see. So means what, there is no nothing will be changes here, again it come back to the same shape and size, it regain its original shape and size. So again this, that's why this point E represents the elastic limit here. Okay, I'll go for this, these are the very important points what we have to remember here. So the very first point P indicates it's a proportionality limit. So in that case, So we can just see the stress and strain. So we can get this here, means what, in this region we can see the Hooke's law, that is the stress is directly proportional to epsilon, that is stress is directly proportional to strain. Okay, now the very next point is, so it's a E. So sorry, this E what I am taking here. So this E represent, it's a elastic limit. Okay, the elastic limit is nothing but what? So once if the material removes the load what you have applied for the material for a member, if you just remove, once if it is come back to the same shape and size, means that limit is called as a elastic limit. For example, if I take some spring here, okay, spring here. Now what happens if you just apply load? Okay, so if you just apply load here, so there will be a elongation takes place. The next case is what? If you just remove this load here, what you have applied, okay, P. So the next thing is, it has to come back to the same shape and size here, like what it has in the previous one. So means what? This property is called as a elastic limit. That will be the elastic range of that particular material. Okay, now this represents the elastic limit that will be that material will be having here. Okay, now, so this is a very important thing here, but this curve will not be a linear, that is from P to A. It's like little bit curve here. Okay, now this is the second point here. Now we'll go for the third one. The third one is, you can just see there will be a Y1 and Y2 will be there. Now what happens before the E? You can just see there will be a the region below this, means the region which is left to this, left of this is called as a some elastic region. So this is called as a elastic region with respect to the point E towards the left hand side. Now if you move beyond the point E, this is called as a plastic region. Okay, this will be called as a plastic region. Now the next thing is, we'll go for the third point, that is called as a Y1 and Y2. I'll just take this is Y1 and Y2. Now what is Y1 and Y2 indicates? Okay, you just see here, this is the E, the beyond the point E, the material starts in a plastic region. The material try to, okay, the material will be acts like some plastic, okay, it exhibits the plastic characteristic. Okay, from the point E, the material will be enters into the plastic region. So plastic region means when you apply load, the material will not be regain its original shape and size beyond the point E. Now what is Y1 and Y2? Because Y1 will be there. Actually what happens, because once if you apply the load, deformation takes place. So away apart, that is beyond the E also, there will be a deformation takes place, means there will be a strain. Okay, now what happens at Y1 is indicate it's a upper yield point. Okay, so this Y2 indicates it's a lower yield point. Now actually these are the upper yield point and the lower yield point. Now what is meant by yielding? The very first thing is, we should come to know what is the meaning of this yielding here. So yielding is nothing but it's something like the material will enters in a plastic region. That indicates the yielding here. Okay, now what happens at point Y1? So this Y1 indicates it is the entry of a member in a plastic region. Okay, this Y1 indicates it's an entry of a material in a plastic region. Obviously that is beyond the point E, it will behave like it is entering in a plastic region. But the thing is when the Y1 comes, okay, okay, the metal try to behaves like a plastic, means it entering the plastic region. Now what happens again, this Y2 is decreases. There will be we can just see here, so Y1 is somewhere here, so this is a Y2 here, because lot of questions will be arises, because once if the deformation takes place, the stress will also be increases. But the thing is, once if Y1 is after Y1, the Y2 will be decreases. Why the graph is such kind? Because the strain will be increases. At the same time, the stress will also be increases. But here it is not possible here. That is from Y1 to Y2. Why the curve will be like that? That is the graph will be decreases. Now for that we'll just take one simple example here. So we have got the, what is the meaning of yielding is nothing but it is something like entry into the, okay, like a plastic region here. Now simple example is, if suppose, so why it is y1 to y2, the curve will be decreases. If suppose if I take a member here, okay, which is having some the crystal structures will be there. So now there will be having some bond will be there between the atoms here. So this is a bond between the atoms. Now if you just apply load on either direction like tensile force or something, so what happens? So you just see this is a member here. So inside this it's represented some atoms here. Atoms are molecules which will be having some bonding here. So now if you just apply this load, what happens? Okay, the member will be elongated. The next thing is, so these are atoms which are having a molecule, they will be having a bonding between each other. They will resist the applied load here. So that's why there will be a stress will be developed here because of the bonding in the atoms which resist the applied load here. The thing is, what happens when the load increases? When the load increases, okay, at some particular point you can just see this bonding will breaks here at some particular, okay, atoms. If this bonding breaks here somewhere here, so what happens? Because initially there will be a stress in the member, because of the bonding between the atoms here, it resists the applied load here. Okay, now this stress will be there now. So once if the load increases, what happens? If suppose there will be a, okay, chances of bonding breaks here, breaking of the bond will be there. Okay, if suppose this region or these two atoms will breaks, so what happens to this four, the next four terms? Only four atoms are there. Okay, four, okay, terms are there. So in that case there will be a stress which is developed inside this body. It will be goes on decreases. Okay, if it goes on decreases means because of this breakage of the bonding between the atoms here, because already these two are broken. Okay, only the four terms are there, because of the four, that is from 6 to 4, there will be a decrease in the strength here. Decrease in the strength means they cannot be resist that much of stress against the applied load or strain. Okay, that's why this stress will be decreases. Okay, because what I am talking here is it is in a plastic region. Okay, in the plastic region, that's why you can just see from y1 to y2 there will be a decrease in the curve here. So which means what? Even though the length increases in the member, there will be a decrease in the stress here, just because of this breaking of the bond here. Okay, it's nothing but, okay, now we'll go for the y2 to u. Okay, now I think you have understood this y1 to y2 here. Now we'll go for the y2 and u. Again there will be a dislocations will be there at point y2 and u. I hope you have understood this. So this is upper yield point, lower yield point. So this is a general example how we can take here. Again now we'll go for the y2 to u here. So y, again there will be an increase in the curve. One thing is it was decreases. Again what happens? Again from point y2 to u, the curve will be increases, means there will be a sudden increase in the stress along with the strain here. Now how it will be looks like, what is the reason behind that? So we'll go here. I'll just take one more example here. If suppose a member is there, if suppose there is a one member here, you can just see these are the, again I can take some of the bonding here. Some members are there, like friends are there. Now these are the 5 members you can just see here, like atoms or anything. Now what happens if you just apply load here P? Now these are under in the plastic region itself, because we are talking about the plastic in the region of plastic here. Okay, now these people will be having somewhat like bonding here again. Okay, why I am telling this? So what is the condition from y2 to u? Why the curve will be increases? I am trying to explain that one. Okay, now initially they will be having the bonding here. Now what happens when the load increases? When the load increases, okay, the bonding between these two will be broken here. So in the next case what happens, so this load, so what you are applying, they'll try to pull these members here, they'll try to pull these members, okay, like 5 members are there, they'll try to pull these members. So at some particular point, so if suppose the bonding here, it will break, so these two people will be fell down here, okay, these two people will fall down, okay, fell down. The next what happens, only 3 members were there, so 3 members were there means, so why the y to u, it has been increases. Now what happens, once if the 2 members will fell down, these 3 people will think that, okay, if suppose these 2 people initially, if we just assume, if this is a P1 is nothing but, so the forces, these are the resisting forces which is offered by these 5 members against the applied force. Because of this applied force, okay, this 5 members will be resisting this applied force. That value what I have taken here is a P, okay. Now once if these 2 members will fall down, okay, only 3 members will be there. The next thing is these 3 members will think that, okay, if you just think that here, these 3 people will be thinking in such a way that if we are only 3, even if we apply only P1 value, like resisting force of P1 value, again we will also fall down, okay. That's why what they will do here, they'll try to apply some more load which is more than this value, okay, they'll apply more load like P2 which is greater than this one, like P1 value. So that's why what happens, this is something like inherent property of a mild steel where it behaves something like here. So initially because of this falling of these 2 bonding here, so only these 3 members, whatever the metal it is left as it is, they will become very stronger than the previous one. So that's why these 3 members, what they'll do, they'll be put some more effort so that they'll be resisting this applied force. Otherwise what happens, this member will be failure takes place, okay. That's why if they are resisting the more force means what, the stress will be again the maximum, again the stress will be increased in the member. That's why there will be a sudden increase in the curve here, that is from y2 to u. So therefore generally what we will take here, the region between from y2 to u, this region is called as a strain hardening. That process is called as strain hardening. This is a very important thing here, that is a strain hardening here. So because you can just see with this example we'll come to know what will be the strain hardening. This is some of the, okay, like one of the inherent property of a mild steel material, okay. Now again why this, so this u is the present the ultimate stress here, this you can just see here, this is called as a ultimate stress. So ultimate stress means only this much amount of force, this much amount of stress it can, the metal can be developed here, okay. After that there will not such kind of stress will be developed inside the body, that will be the maximum stress which can created in the body, okay. So that's why this ultimate stress will be the maximum stress that you can find in the member. Now what happens, again the stress will be decreases. How it is possible? So already it is more strength, more load is acting, more, okay, more stress will be producing against the applied load. So again there will be decreases in the curve. Decreases in the curve means what happens, again there will be a strain will be increases, again there will be a strain will be increases. So means what, again you are applying a load, because of that applying load only increase in the strain will be there. But so here there will be a decrease in the stress. Why it is so? So here there will be a more, they are producing more stress against the applied load. The next thing is why it is so means, because everyone is, okay, everyone will be having some kind of capacity. After that definitely everyone has to be in it has to reach to the failure point. So even if the more load is applied, so what happens, this member will also become a failure takes place. Here also he will also failure takes place. He means here this member will also that is a he will also breaks here. So what happens, at some particular point when it reaches to a particular point, so this member will also fall down here, okay. That's why they will not be having again that much amount of stress to resist this applied load or something like strain here. That's why this graph will become a down here. Now very important concept is, so what happens to the material when the material is at point U? Okay, now here the material is in a that is the elastic region itself. It doesn't even if you apply load, remove the load, it come back to the same shape and size. Okay, after E, it will be enters in a plastic region. There will be upper yield point, lower yield point is there, where the dislocations will be start. Dislocation means there will be a dislocations in the atom, that is a breakage of the atoms. Now from Y2 to U, so why it is happening? Because of the strain hardening, because of the when if the lose up when some atoms broken here, the other members will be, they will produce some of the more efforts here, so there will be a more resistance that is which resists this strain here. Now after point U, so this point U is nothing but it's a ultimate, if you are doing with the tensile stress, so it is called as ultimate tensile stress here. So now what happens at point U? Why it is maximum? Okay, so just before this, just before this, the material is a harder one. Now if I take this member initially, okay, if it is subjected to a load P, so when the member reaches to U, that is ultimate tensile stress, so it's nothing but after that the curve will be decreases. So at point U, you can just see the member will be like this. Means what? There will be a formation of the cup, like okay. So this region you can just see. This phenomena is called necking here. So this phenomena is necking means when the member reaches to ultimate tensile stress, there will be a formation of the necking here. Okay, so this formation of the necking means, so after this point U, now the point U indicates this is the initiation of the necking here. Okay, that is a necking means decrease in the cross sectional area. So decrease in the cross sectional area. Now, so after this necking operation here, because when it reaches to the necking here, we don't know, because this member will be failure to take place, means at any point the fracture can be take place, at any point okay, this member will be breaks here. That's why this is inevitable that this member will be failure can be take place at any point after when it reaches to the point U. So now at point U, the member is subjected to a phenomena called necking, where the completely the decrease in the diameter of a means lateral dimensions will be decreases here. Okay, so now this is the main one of the concept where which behaves like a at point, that is ultimate tensile stress. Now after point F, so it means after point U, that is ultimate tensile stress, the material will breaks at any time. Okay, so it behaves something like a smoother one, that is this region that is from U to F is called as a geometrical softening. Okay, I hope you have understood this. Now very important thing is this, what we have drawn this graph, it is called as a theoretical graph. Okay, this is not the actual graph. Okay, so actual graph means, so up to Y2 you can just see the same property of a material. Okay, we can just see up to Y2, so we can just see the same graph, because when you go for the stresses, we'll be having a two types of stresses there. So one is P, sigma is equal to P by A. Okay, this P by A is generally called as a engineering stress here. So this is called as some engineering stress. Okay, so where A is nothing but area of a cross section. For calculation purpose, what we are doing here, so this area we are taking it as a constant here, means throughout the calculation purpose the original cross section we are taking. So that's why it is called as a engineering stress. Okay, now the corresponding strain is called as engineering strain. Now the second one is, I'll take sigma dash is equal to P by A dash. So the P is nothing but P will be varies because we are applying gradually the load. Okay, but the thing is the diameter, because the area will be changes here, but in this one the area will be remain same. The area will be remain same means what here, for entire calculation we are taking the same cross sectional area, but for this one sigma dash is equal to P by A dash, so we are not taking the original cross sectional area here. So that's why, so this A dash indicates it's a instantaneous cross sectional area, means at any particular time what will be the cross section of that material. Okay, if suppose if I'm taking the necking one, so what is the cross sectional area, that is the lateral dimensions at some particular necking here. Okay, by taking that diameter or that dimensions, I have to calculate the area A dash. Okay, it indicates what A dash, it's a instantaneous cross sectional area. It is nothing but, so this sigma dash indicates it's a true stress here. So this will be the true stress here. So how these two are related here? Now we can just see here, when the member that is from point Y2, these two things, that is a engineering stress and the true stress, both are same. But the thing is, that is from point Y2, that is at from the point lower yield point, what happens, this true stress will be completely changes here. It's something like it becomes in this manner. Now this is a true fracture. This is a true fracture, but this F indicates this is a fracture point. This is a fracture point actually, that is for a theoretical graph. But in reality, this will be the true graph of a stress strain. Somewhere here you can just see the fracture point here, that is a true fracture. Now why you can just see these two differences here? Because if you take this here, the load, if suppose if you are applying constant load here also, but the thing is here it's a constant. Okay, the thing is what, if suppose if it is a 20 kilonewton, if this is a area something, you are getting constant here because of the diameter. So this will be getting some answer here, that is the stress. The next step is what, again the area, you are applying a more load, the area will be the same thing. Okay, means what, there will be a stress will be increases. But in this condition, so again here the load is also increases. The next point is why there is a difference between these two, that is a curve here, that is for a theoretical graph, and this theoretical graph and that is a true graph here, that is from the point Y2. So generally what we will be having, we are having a P is, that is a sigma is equal to P by area, that is a stress is equal to load by area. Actually this, in this formula what we are taking here is for calculation purpose, for engineering calculation purpose. So this area will be that is a this area will be a constant one. Constant means depends on the original dimensions. We are taking this cross sectional area will be remain same throughout the calculation purpose. If suppose the load is applied 50 kilonewton, if the diameter of the member is suppose 20 mm, but throughout the calculation this area, cross sectional area will be remain same. Only thing is the load will be varies. Here the load will be increases. Again the thing is here the diameter is something like, okay, it is remains same. So this is called as a engineering stress here. We are not changing the actual cross sectional area in that some particular point where the applied load. Okay, now the corresponding strain is called engineering strain. Okay, there will be other one more stress is there, that is the sigma dash is equal to P by A dash here. So where A dash indicates here, because these two are the different here. Okay, now where A dash indicates it's a instantaneous cross sectional area. Now why we are taking this instantaneous cross sectional area means, if suppose, okay, when the crack takes place, like when the member is in this range, like during the necking, so the diameter will be decreases here. Okay, now with this with this load, I need to take this cross sectional dimension, that is a cross sectional area we have to take. So means what, in that case what happens, here the numerator will be maximum, but the thing is the A dash, that is a cross sectional area will be decreases because of this decrease in the diameter, that is a lateral dimensions. So once if the numerator increases, the denominator decreases here. Okay, because of the instantaneous cross sectional area. So therefore this stress is called as a true stress actually. Okay, this will be called as a true stress here. Now this true stress will be increases when we compare to the engineering stress. That's why, that is from point Y2, this black color indicates it's a engineering stress value. Okay, this green color indicates there will be a true stress, which is always it will be increases. That's why the fracture point you can just see somewhere here for the theoretical graph. Okay, but the thing is, actually in the true nature, the failure can be takes place somewhere here. Okay, if you like this video, please comment, share it to your friends, and subscribe to our channel. Thank you.